Mr. Collier, and today we're doing some probability distributions. So we're looking at, there's some definitions. First, a discrete random variable x. So sometimes we like to call a probability x, and we call it a discrete random variable x if the values that are possible are discrete values and not continuous. Okay, so let's take a look. Now we use capital X for these discrete random variables and x to represent a particular possible outcome. So in this table here, we're talking about rolling a die, and you win €1 if you roll a 3 or less. So that's if you roll a 1, 2, or a 3. So the probability of that happening is half, or 3 out of 6. Leave it as 3 over 6. And the outcome is the x, so the outcome is actually €1. Okay, and if you win €2, that's if you get a 4 or 5, so that's 2 out of 6 is the probability. And you get €10, so I'm going to put a 10 over here. €10 if you roll a 6, and that happens with 1/6 probability. So this is called the probability distribution table, and it's very common to have these types of questions, but it's just organized into a table. Notice the probabilities have to add up to 1, so this matches, otherwise it's not a probability distribution. Okay, so basically a probability distribution, it has to list every single probability that happens in this case, and these have to equal to 1. So let's draw the probabilities here. We have blue or red. We got a bag with 4 blue, 2 red, and the probability of getting blue here is 4/6, and red is 2/6. And on the second go, this is without replacement, so the blue one's taken, is gone. Then we have five counters, and 3 of them are blue, so it would be 3 out of 5. Okay, and this one here would be 2 out of 5, and then we have blue, red. If 1 red is picked, then there's 1 red left for the second pick out of 5 total, and this one is still 4 blue, so it's going to be 4 out of 5. So those are our probabilities. Now in part B, we're going to work out the probability of 2 blue counters. That's blue on the first one, blue on the second one. Okay, that's going to be this branch here, blue, blue, so it's going to be 4 over 6 times 3 out of 5, which equals 12 out of 30, which is 40% if you type that into your calculator. Okay, next we got the random variable b, which is a bit confusing because we used b before to stand for blue. But the random variable b stands for the total number of blue counters drawn, so the total. So what's the probability the total number of blue counters is 2? Well, that's the same probability. That's the probability of blue, blue. So probability b equals 1. That's going to be the first one's blue, the second one's red, plus the first one's red, the second one's blue. That's exactly 1 blue. So that probability is 4 out of 6 times 2 out of 5. Blue, red, yes, plus this branch here, 2/6 times 4/5. That gives you 16 over 30. Okay, that's the probability. The probability of exactly 1 blue, or in other words, 1 blue and 1 red. Okay, next we're going to put this into a probability distribution table. So we just worked out probability b equals 2. That was 12 out of 30. And this one's 16 out of 30. Those add up to 28 out of 30. So this one, we can do the math, but we know this has to be 2 out of 30 because they have to add up to 1. We can double check that with the tree diagram. So 0 blues means red, red. So 2/6 times 1/5 is indeed 2 out of 30, so it's correct. Okay, next we're going to put it into a bar chart where this is the probabilities. Oh, maybe I could write, yes, sorry. Let's write it like this. Probability b equals b, and this is b over here. So b can only be 0, 1, 2. And yes, we're going to draw it so that the height of each bar is the probability. So I'm going to draw this up at 2. I'm not going to draw this to scale because there wouldn't be enough room. So the probability of 1 should be up at 16. And this should be at 12. Okay, so that's what the bar graph looks like. The experiment above, actually, sorry, on this vertical axis, I should probably have written fractions, of course. Okay, so the experiment above is repeated 60 times. Estimate the number of times there would be at least one blue counter. At least one means 1 or 2. So that is the sum of those together. The probability of that happening is 28 out of 30. Okay, so we do 60. The expected value equals 60 times 28 out of 30, which equals 56 times. We would expect it to happen 56 times. Okay, for the next question, x is a random discrete random variable such that the probability of x equals kx for each of these. Well, maybe that's a bit confusing, but let's just make the diagram to see what we're talking about here. Probability distribution. So the x's are 1, 2, 3, 4, and the probabilities are k times x, so k times 1, or 1k, 2k, 3k, 4k. So that's all we're talking about here. And the way to figure out what k is all the probabilities have to add up to 1, or 100%. 1k plus 2k plus 3k plus 4k equals 1. So 10k equals 1, k equals 1/10. Okay, so then we can write down the actual probability distribution. So it's 1, 2, 3, 4. And k is 1/10, so we're going to have 1/10, 2/10, 3/10, 4/10, and all those add up to 1. Find the probability x is between 2 and 4, but not including 4. There's no equal sign there. So this is the same as the probability of x being between 2 and 3, or 2 and just the values 2 or 3. And that is, of course, just 5/10. You add those two together, or half, or 50%, if you will. Okay, a cumulative distribution function means a probability up to that point, so less than or equal to a certain value. So that's going to look a little bit different here. This is going to be x, and I'm just going to write p here. I'm not sure what notation to use, but the probability, the cumulative probability, is what we're going to be putting in that row. Okay, so this is 1/10, and the probability x is less than or equal to 2. We add these two together, and we get 3/10. And then up to 3, we get 6/10. And then probably less than or equal to 4 is obviously 10/10. So they don't add up to 1 in this case. It's just that the last one has to be always 1. Okay, the last one has to be 1. All right, so expectation, we talked about it a little bit here, is the expected amount or expected value. This is often written as expected value of x. So let's take a look at this example. The probability of a person in a particular town carrying a mobile phone is 1/3. In a sample of 150, how many would you expect to be carrying a mobile phone? Well, that's obviously 1/3 of 150, which equals 50 people. Okay, we just multiply the probability times the number of people, right? So that's what we do when we're doing expected value. So let's consider a game of chance, and this is the probability distribution. Find how much you would expect to win per game on average if you played 600 times. So the expected value, this is if we play once, is going to be 1 times half plus 2 times a third, because there's a third chance of winning $2, or 10 times 1/6, because there's a 1/6 chance of winning $10. Okay, and if you work that out, you get 17 over 6, which equals about 283. So for 600 times, we do 600 times 17 over 6, which is actually 1700. Use your answer in part A to calculate how much you expect to win if you play the game 12 times. Okay? So it's just the same thing, just 12 times 17 over 6, which equals $34. I think it's dollars, right? I can't remember. Okay, a fair game is when the expected gain is equal to 0. That means the house doesn't win or the person playing doesn't win. It should all even out. So find out how much the owner of the game should charge for this to be a fair game. Well, we saw that expected value is 283. That means on average, they gain €2.83 every time they play. So the owner should charge, obviously, €2.80. Okay, so that means they would on average earn 0, and that would be a fair game. Okay, this is the formula from the formula booklet. This is kind of what we did up here. We did x times the probability of x plus x times the probability of x plus x times the probability of x. So that's what this is saying here. This is sum, and this is x times probability of x occurring. Probability of x occurring. But that's what it looks like in the form of the booklet. You just multiply the values from your probability distribution table. Okay, so let's take a look at this one here. This might look confusing at the beginning, but this is from question 2. So remember we had in question 2, 1, 2, 3, 4, and then here we had 1/10, 2/10, 3/10, 4/10. So the expected value here is we take each x and multiply by the probability, and then add those all together. So we do this here to work out the expected value, which is the amount you would expect to get on average. Okay, so if we do that and work it all out, I believe you get just exactly 3. So that's the average amount that you would get. Okay, let's look at the let's skip this one here and go straight to the last example. Okay, so we're rolling a die, and all these probabilities are 1/6. There's a 1/6 chance of rolling a 1, 2, 3, 4, 5, and 6 is an equal chance for each side of the die. Assume it's a regular die, determine whether it's a fair game. Okay, so let's get the expected value. Expected value is 1 times 1/6. And these are zeros, so we don't need to include those. Okay, we need to multiply these things together, right? We get €1 for rolling a 4, so that's 1 times 1/6. And over here you get €10 for rolling a 6, so that's 10 times 1/6. And this equals 2, which equals the amount that you pay. So therefore, it's a fair game.